Hello everyone, welcome to my home. Today we're just going to be going over some math. This is going to be the second test on derivatives that I gave right before winter break. And people didn't do so great on it, so we're just going to have it, I'll solve each problem for you so that you know how it goes. This is broken up into 3 parts, so each part corresponds with a page of the test front and back. And we'll get started. So, first question is, a particle's position is given by x of t equals t minus a times t minus b. Now this was a clarification that I didn't realize I had to make until maybe a little bit later, but I should note that a and b are both constants. We just don't know what they are. When is the particle at rest? Now, at rest, we take to mean the velocity of the particle is equal to 0, which means, since we know that the velocity is the derivative of the position, dx dt has to be 0. So we look at this and we find dx dt. dx dt is equal to, this is a textbook product rule case. We have t minus a multiplied by t minus b. So we take the first expression, t minus a, and we multiply it by the derivative of the second. Now, the derivative of t minus b, derivative of t is 1, derivative of b is 0, so this is just 1. Similarly, when we add, to finish off the product rule, we take the second expression, t minus b, and multiply by the derivative of the first, which is also 1. So, with this added information, that this derivative is equal to 0, we have that 0 equals t minus a plus t minus b. With a little bit of arithmetic, you will find that a plus b equals 2t, and so t, or when, is equal to a plus b over 2. That is our answer. Now, did you need calculus to find this? No, you didn't need calculus to find this. If you recognize that this is quadratic, and it's given in factored form, so it has roots when t equals a and t equals b. If you have a position quadratic, it's going to look like this. The time when it's at rest is the vertex, which is always halfway in between the roots. So for that vertex, that's the average of the 2 roots, which is a plus b over 2. And that's how you do it without calculus. Not everything needs calculus. This one didn't, but of course, calculus is pretty quick. Second, now, we're going to analyze this as we go. The radius of a circle is increasing at a steady rate. So we have a circle. It has a radius. Its radius is increasing at a steady rate. Steady, we take to mean constant, not varying. But since it's increasing, it's a non-zero constant. So we just going to pretend that we're German for a little bit and say k for constant. At a certain instance, the rate of increase of the circle's area. So if area is a, the rate of increase we represent with dA dt. The rate of increase of the circle area is twice the rate of increase of the circumference. So is twice the rate of increase of the circumference. I'm using capital C for circumference. So this is our unifying fact. We need to find A and C in terms of R to get all of this together. Luckily, most people should know that. The area of a circle is, of course, pi times the radius squared. The circumference of a circle is, of course, 2 pi times the radius. From this, we have that dA dt is 2 pi r dr dt. From this, we have 2, when we sub in, that will be 2 pi times dr dt. Now, we can multiply out a little bit. 2 pi r dr dt equals 4 pi dr dt. And you might notice something when you start to simplify. A lot of things are just multiplied on both sides. So if you divide both sides by dr dt, that goes away. If you divide both sides by pi, that goes away. Divide both sides by 2, we get that r equals 4 divided by 2, which is just 2. All right. And that's it. There's not much more to say about that one. All right. So, third one, we have the setup. The function g of x is continuous on a closed interval from 1 to 20 and differentiable on the open interval of 1 to 20. So this is a very conspicuous start, giving us continuous on closed and differentiable on open. What we note in terms of like important theorems is that the mean value theorem is applicable. So that's in play. We can use it. We might not need to, but we should notice that we did. And whoever wrote this problem made special effort to show that. And has values given by the following table. So we have a table with x's. They're not really evenly spaced. We have g's, large gaps. We only have a little snapshot. So it's not a whole lot, but we'll come back to that. Does G have a horizontal tangent line on the interval shown? Now, horizontal tangent line, from our perspective, we're going to interpret that as G prime of x equals 0. So is there a spot where the derivative equals 0? And we have to justify our answer. Well, we're going to go back to the fact that the mean value theorem applies, right? If we can find a space, find an interval where the average rate of change, g of b minus g of a over b minus a, we find where the average rate of change equals 0, that guarantees g prime equals 0 somewhere between a and b. And we look at the table, and when x is 1, g is 14, and when x is 10, g is 14. So because of that, by the mean value theorem, since the slope between x equals 1 and x equals 10 is 0, there is some c between 1 and 10 where the derivative of g at c equals 0, thus a horizontal tangent line. So there's two parts to this problem. Recognizing that with this setup, this is a mean value theorem, or at least the mean value theorem is probably important, and then using your words to justify. This is one good justification. There are certainly others. I was pretty liberal with what I took as a good justification on this. It helps to mention the mean value, it helps to mention the mean value theorem, but other things from calculus do apply here. Okay, got a related rate problem. A 5-foot tall woman is walking away from a 20-foot tall street lamp at a rate of 3 feet per second. At what rate is her shadow lengthening when she is 15 feet from the base of the lamp? So, when you're doing related rate problems, draw a picture. Anything that stays still, or doesn't change rather, like the height of a woman doesn't usually change that much, or the height of a lamp, that you label with what it is. So here's our lamp, and here's our woman. And then you draw so that you have everything else. So she's walking away from the street lamp, so we should have a distance between her and the street lamp. Now, you try to avoid using D's, so I'm going to use a lowercase l. And then we're interested in her shadow, so we're going to draw some light from the lamp to her, to the ground, from her feet to where we just drew. That has to be her shadow, right? So we have this situation. We know, of course, that dl dt is equal to 3. We also know that L at this point is equal to 15. And so let's see what else we know. We need some kind of relationship between S and L before we can actually do this. So I'm going to pick out the similar triangle relationship. This tiny triangle here is similar to the big triangle here. So we'll set up a ratio. The ratio between two sides of the small triangle, S and R5, is equal to the corresponding sides of the large triangle. So the side that corresponds with S in the large triangle is L plus S. The side that corresponds with 5 in the large triangle is 20. And then we want ds dt. Now, we could take the derivative of both sides of this implicitly right now. I'm going to do a little bit of algebra because it's going to make it a lot nicer. If we multiply both sides by 20, 20 divided by 20 leaves this free and clear. 20 divided by 5, that's of course 4. Do a little bit more algebra, and we get that 3s equals L, which would be great if we wanted L. We don't really want L. We just want, we don't want S. We want ds dt. So we take the derivative. This must mean that 3 ds dt equals dl dt. Since we know dl dt is 3, we know that 3 ds dt equals 3, so that means ds dt equals 1. If you want to put a unit, it's feet per second. And that would be great. It's kind of interesting. This is very simple because ds dt doesn't actually depend on when you take it. As long as she's going at 3 feet per second, ds dt is going to always be 1 foot per second. So that makes this nice. It's a nice one. All right. This is, I think, the second to last one. We'll find out. So for time greater than 0, so we're not interested in any negatives, particle's position is given by s of t is equal to sine of t minus cosine of t. What is the particle's acceleration the first time the velocity is 0? Now, I noticed that there were some questions on the first time. Because sine is periodic, cosine is periodic, there's actually an infinite number of times when the velocity equals 0. We're just interested in the first one. So we're going to generate some velocity functions. The velocity of a particle is the first derivative of the position, which the derivative sign is cosine of t, and the derivative cosine is negative sine. With that minus in place, it becomes plus sine of t. We're also going to be interested in the acceleration, so we might as well do that now. The acceleration in terms of time is the derivative of the velocity in terms of time. So derivative cosine is negative sine of t, and then the derivative sine is cosine. Great. So we are interested in the first time the velocity equals 0. If the velocity equals 0, that means that, say, sine of t equals the negative cosine of t. Why not? So they should be equal except for a negative sign. They're opposite signs. If we think back to our unit circle, the times when sine and cosine are equal in magnitude is at the pi over 4s. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. The first time when they're equal in magnitude, but opposite in sign, is here, over at 3 pi over 4. That is our t. But that's not the answer. The answer is, what is the acceleration when t is 3 pi over 4? So we go back to our acceleration. We want the negative sign of 3 pi over 4 plus the cosine of 3 pi over 4. Evaluating these, we get negative the square root of 2 over 2 plus cosine is negative the square root of 2 over 2. Add these together, you get the negative square root of 2. Again, having the unit circle, very helpful for something like this. All right, this is the last one. And fittingly, it's the hardest one, or requires the most stuff out of you. We have an expression of the results of an implicit differentiation. We have x plus 2y times dy dx equals 2x minus y. And we're asking what is the value of the second derivative of y at, or second derivative of y in terms of x. And they ask at a particular number, so that's, or set of y and x. So that'll simplify things later. First thing we want to do is, as a side note, make this so that we have dy dx by itself. We're not going to use that for the meat of the problem, but it's nice to know. So dy dx is going to equal 2x minus y over 2y. And then if you use our numbers here, which you should, this, of course, is going to equal 2 times 3 minus 0 over 3, which is just going to be 2. Not our final thing. We'll keep that in mind. Go over here. Now, this is what implicit differentiation is made for, so we're going to do it. The first part is a product rule again. So we'll take the first, x plus 2y, times the derivative of the second, which is second derivative, plus the second dy dx times the derivative of the first, which is 1 plus 2 dy dx, equals, derivative of this implicitly, is 2 minus dy dx. Now we couldn't use the specific value before, because otherwise it just gets 0 equals 0, and no one would be happy. But at this point, now that we've successfully taken the derivative, before we do all the arithmetic garbage with a lot of symbols and a lot of chances for you to mess up, now is the time to sub in the actual values. So x is 3, y is 0, and dy dx is 2. So we have 3 plus 2 times 0 times the second derivative of y in terms of x, plus 2 times 1 plus 2 times 2 equals 2 minus 2. Right, and then we just kind of simplify. 3 times what we want plus 2 times 2 is 4, 5, 10 equals 0. 3 times the second derivative of y in terms of x is equal to negative 10. So that means d squared y over dx squared, what we wanted, equals negative 10 over 3. And that is it for the first part. That was the first 6 problems. Join me on the next one to get the next 2 pages. Thanks for stopping by.